Good evening, everyone. I'm Calvin Joseph, and today I'll conduct your week 11 problem solving and doubt clearing session for the course Control and Tuning Methods in Switch Mode Power Converters. So today we'll be discussing a lot about large signal controller tuning, etc. So we'll be looking into the following, like what is a PID controller? You have been already taught what is PID controller, etc. This is just a brief recap regarding PID controller, and then how do we link a switching surface with a PID controller. Then what is large signal controller tuning, then what is dynamic voltage scaling, and then we will do some questions. Okay, so to start over here. This is your week 11. Okay, so we are first starting with the PID controller. So can you tell me what is the transfer function of a PID controller?
Kp plus Ki by S plus Kd into S.
Okay. Okay, so this is your controller transfer function. Okay, so over here, there is a term which is problematic. What term do you think it is?
Derivative term.
Yes. So your derivative term, if you just have your g derivative of s, that is kd into s. So this is in this one, the order of the numerator is 1, but the order of the denominator is 0. So such a transfer function is not practically possible to implement. So what is done is, we add one derivative filter, like a low pass filter to it, with some time constant tau d, which that becomes realizable. So this is the ideal one. It is not practically realizable. So the one which we use, the practical one is Kp plus Ki by S plus Kds upon 1 plus tau S. Okay. So this is your practical PID controller. So how many of you have used a PID controller anytime in your projects or in anything, or your simulations?
In simulations used.
Okay. Like which simulation did you do?
A grid connected voltage source inverter, DQ control. So in that PI controller was used.
Okay. And what about others? Have you used PID controller anywhere else? Okay. So PID is relatively new. So the PID controller is used in a lot of places. Like PID controller is very good. It's like very robust. It would work. Usually it would work. So what you have in a PID is, you have a gain Kp, this your proportional part, right? Then you have your integrator 1 by S, and then you have your gain for your integrator Ki. Okay. Then you have your S upon 1 plus tau S. Then you have your Kd, that is your derivative gain. And this is additive. So this is your overall input. Okay. So this is your input and this is your output. Now, in now control system, let us talk in perspective of a control system. What do we have? We have a reference. Okay. We subtract it from our feedback. Then you get an error. That goes to your controller, that is your PID controller. Then you get some output, not output, you can say VCON, like your control output, that goes to your plant. There could be an actuator as well, and this is your output. And then you have what is known as your sensor, and this comes over here. Okay, so this is your PID controller. So the objective of your PID controller is to make your error zero. This is one objective of your PID controller. What do you think would be another objective for a controller? What should it be able to do? Like you're using a PID controller, what do you want your PID controller to do? In control systems, your objective is what? You want to make this error zero. That is one of the objectives. What could be another objective?
The transient performance,
Right.
uh, dynamic performance of the plant.
Yes. So you want about the dynamic performance. What do you mean by dynamic performance is, suppose your reference was 1 volt, your reference now is shifted to 1.2 volt. Okay. So now assume your controller is working, closed loop is working. So your output voltage is like this, like this, like this. It is there. It is a steady state, it is 1 volt. Now it could go like this to 1.2 volt. It could go, it could go like this, like this. It could go like this. It could go orange. It could go like this. It could go. It could go in both ways. In not both ways, in many ways. Okay. So your objective is, one of your objectives is to design this performance, how it will react when you're changing your reference, how it will react. That is one of your objectives. Okay. And so what we are doing is, like the reference over here, you are changing it. You're giving a change in your reference. That is, earlier you wanted your DC-DC converter to regulate your output voltage at 1 volt. Now let us say you wanted to regulate at 2 volt. Okay, this could be one of the things which happens. So then what will happen? So now your reference was 1 volt and your error was 0. Right? Let us take one case, only one case, make it easier to understand. So we draw here. So your reference was like this, and your output was matching. This matching. That means your error was 0. Now your reference changes, your output will change like this. So we will let us draw how the error will look like. Error was initially 0. Now will the error be positive or negative? Till this point, your error was 0, right? Now your, let me label. So blue one is your reference. This is your output. So now when your reference changes and your output is trying to reach that new reference, what will be the error?
When output is less than reference, error is positive.
Okay. So your error will be like this. Error was initially 0. Then your error, it is positive. Your error suddenly becomes positive. Large step. Because your reference has changed drastically. the output that cannot respond immediately, so your error is positive. Then it will slowly till this point will reach zero at this point. Okay. Then your error will become negative. And then again it will go like this. Finally it will settle. So this is how your error will look like. So when you suddenly change your reference, your error will suddenly become, there'll be a jump in your error. And then as your output slowly comes close to the desired reference, your error also becomes zero. Then it will, because your output has further increased above your reference, your error becomes negative. Then again, like that, it finally will settle. Okay. So this is your control. Like this is how your output will look like, and this is your error. Now, your error is being fed over here, right? Your error is going over here. So what will the proportional part do? The proportional part would be just a multiplication of the error. It is just Kp into error. Okay. And your integral part, what do you think an integrator does? Like what it would do? If you give such an input to your integrator, that is your error is your input to your integrator, how will your output of your integrator look like?
Area under that error curve. It will
Correct.
sum.
So, suppose your integrator was at some particular value. So it was at some particular value. Then it will accumulate. When error goes negative, it will slowly reduce a little. It will increase, reduce. Like that, it will go on. Finally, it will settle at some value. So this is your output of your integrator. Okay. Proportional is just a scale version of your error. Integrator is a accumulation of the errors. And what is the output of the derivative? What is the output of the derivative? Let us forget the filter. Filter of the derivative, just talk for an ideal derivative. How will the error look like? How will the derivative into the error look like?
At t equal to 0, there's a discontinuity.
Yes. So, we will drop out these things. Okay. If derivative is 0, suddenly it will have a spike because there's a step jump in error. There's a step kick. That's not a derivative kick. Okay, so your error has increased drastically, and because of that, your derivative action is increased, and then what would happen? It is kd into your derivative of your error. So it would reduce. It would reduce. But would it be negative or positive? There's a jump over here. But then I'm thinking afterwards it will be negative because from this point to this point, the value has reduced, right? So the d error 1 minus error 0 upon dt. So it would be negative. So it would go to negative. It would be negative. Then from here to here also it would be negative, but some value like that. It would go. Finally, when it would go on reducing, sorry, till this point, your derivative will be negative. Then once your error starts increasing, your derivative will be positive. Till this point. Till which point it will be positive? Till this point. To this point, it will be positive. Then again, it will go less than 0. So we have to check this. I have to check this. Just I think a simulation would be best to understand this. But this is something like this. Okay. Any doubts in this? You want me to explain something? Oh, okay. So what will happen in steady state is, so what does your proportional do? What does your integrator do? What does your derivative do? So which one is objective is to improve your dynamic performance? Which of the PID is needed for improving the dynamic performance? That is your transient response. Which one is instrumental and useful?
Proportional.
Okay, proportional also is useful, yes. What about derivative?
Derivative also. Derivative will affect this peak overshoot and the settling time.
Yes, yes. So the derivative, it introduces damping in your system. So all these peaks, right? It will reduce all these peaks and it will make your output reach fast. That's the job of the derivative. What's the job of the integrator is? It will make your steady state error zero. Its job is to make the steady state error zero. Okay. Because if you think in your control system, suppose let us remove this step. Let us say, sorry, your reference suppose is 1 volt and your output also is 1 volt. It's working fine. Your error is zero. Then how much will be your VCon? If your VCon also is zero, then how will your plant work? It cannot work, right? Or how does it work? If your output is 1 volt, your reference is 1 volt, error is zero, then how will your plant run?
There will be a steady state part of the control signal.
Okay, and where does that steady state part of the control signal come? Because if you see in the derivative also, if I draw formally, finally derivative is zero. Finally, your error also is zero. So your KP into error also is zero. So the steady state control input is just because of the integrator. The steady state beacon, this is due to your integrator. Hmm? This also silence. What
Uh,
about Joshi?
Sir, is it
Yeah.
because that integrator gain becomes infinity at a steady state? That
No, no, no.
is
Integrator gain does not become infinity. Integrator gain is integrator gain. But the accumulated
effect
value,
of that effect ki by s tends to infinity when s tends to 0.
yes. Oh,
Uh,
yes, yes. Kind of. We can say, let's say, this is your error. Suppose your error is zero, right? Your error is zero. So gain into zero is zero, right? Your you assume your error has been zero for a lot of time. Then this derivative of this straight line also would be zero, right? So this also would be zero. So now what is actually happening is In your integrator, there's something known as an initial condition. An initial condition. Like assume your integrator had a value. Let us say it had a value 5. It had a value 5. When your error was changing everything, and finally your error becomes 0. Once your error becomes 0, the output of your integrator will be 5 and it will remain at 5. It will not change. So your output of your integrator will be 5 and this will be from 5 into ki. Okay. So what happens is the integrator reaches some value. It reaches some particular value. It reaches that particular vcon which is you require such that you get your output. Your output is as desired. So the final accumulated value of your integrator has to be this vcon desired. Then only your output will be at the desired value. Till suppose it is vcon desired -1, then your output will be output desired some -5 or some value. As long as that is there, what will happen? There will be some error, the output will be there, something, and it will try to correct until your output of your vcon becomes this vcon desired and your output will become output desired. So that is why your integrator is the one which is linked for removing your steady state error. The integrator is the one which causes the elimination of your steady state error. I think such a thing would be best to simulate and show you guys. So once we are done with the questions, everything, we'll do simulations and we'll check this. Okay. But if you have any doubts, now you can still ask. Hmm? Okay.
It's clear, sir.
Okay. Maybe we'll try with a certain this. Okay. So now let us. Okay. So you have your PID controller and you have what is known as steady state error. That is one thing you look at. You look at what is your percentage overshoot, like how much it overshoots that. Then finally, what is your settling time? So these are things which you are looking into, which you are considering, and accordingly, your KP, KI, KD will affect that. How your KP, KI, KD has an effect on your steady state error, how it has an effect on your percentage overshoot, your settling time, etc. That is there. That sir has also shown in his lectures. It is there. That also I have just put it over here. Okay, I've just shown it over here. So if you will see this, I have listed the three PID gains. You have your KP, KI, KD. If you increase your KP, then your overshoot will increase. If you increase your KP, it doesn't have that much impact on your settling time. But if you increase your KP, your steady state error will reduce. Okay, it will decrease. If your steady state error with KP 10 was some value, if you increase KP, your steady state error can reduce. That is there. Now, what does your integrator do? Integrator is mainly there to reduce your steady state error. To make your steady state error zero. That's the beauty of your integrator. But what it does is, it will increase your settling time, it will increase your percentage overshoot. So in the dynamic performance and all that, your integrator has slightly a negative effect. But in your steady state error, in your final settling value, integrator is a must. Okay, because you really want to get rid of your steady state error. So for that, you have your KI. Then the derivative, as you have seen, in steady state, KD, because in steady state, what happens? Your error is zero. The change in your error also is zero. So it has a negligible impact in steady state. What it does is derivative acts like a kind of like a damping. What is a damping is it will that overshoots which you see, that is like these kinds of these overshoots, like this overshoot, that it will try to reduce. It will try to it improves the damping, so it will reduce your overshoot to become like this. And it also can improve your settling time. It could also reduce your settling time. Okay. So this is what was there regarding your PID controller. And PID controller is a very extensive topic, and you best understand PID controller when you start working with PID controllers in your simulations as well as in your practical setups as well. Okay. Okay. So after that, you have learned about two types of uh, like optimal transients, right? You have one is your load transient, one you have is your reference transient. Okay. So in your buck converter, which we are going to consider extensively, what happens is, let me draw it. This is your input. This is your switch Q. This is your Q bar. This is your L, C, and load resistance R. LCR. Okay. So in steady state, your inductor current will be something like this. Your your output voltage would be it would be something like this. Okay, let us say it's not drawn to scale. Let us say this average value is 5 ampere and this average voltage is 1 volt. Okay. This is your V output. This is your IL. So if you draw the phase plane, this is your V output. So around 1 volt and around 5 ampere will rise, fall. Like this, it will look like. This is your IL, this is your V output. So let me draw in different colors to make more sense. Mhm. So this is the case when your current is rising. This case, sorry. This is the case when your current is falling. this how it looks. You must keep in mind that there's a on and the blue one is the off. So the average value is 5 ampere and 1 volt. But the instantaneous value is not 5 ampere and 1 volt. Over a switching period, the average value is 1 volt and 5 ampere. But at each instantaneous value, it is not that value. Okay. Now, you want to increase your load from 5 ampere to, let us say, 10 ampere. Right? But you want the voltage to remain the same. The new operating point is somewhere here. This is your new operating point. So you want it to operate from here and here. Once it reaches it, it should work in this part, right? It should rise, fall, rise, fall. Now, you want it to go from this part, from this point, from here, you want it to go here. I'm so sorry. So what you would do is, you would turn it on. It will go on like this to this point, reach some value, and from here, you turn it off. That means you just turn it on once, you just switch it off once. This is your best control. So this is known as what is your time optimal. This type of control will take your lowest amount of time. So you do go to one operating point to your next operating point. Okay. So this is your phase plane for load change. Okay. Now, I want you all to tell me, assume you want your current to be 5 ampere and you want your voltage to be 1 volt. So again, it will look like this. It will rise like this. It will fall like this, right? Now, you tell me, you want your voltage to change from 1 volt to 1.2 volt. Then where should I draw? Voltage has to become 1.2 volt. Then what should change? So that means your new operating point is here. It is this point. So it will steady state will go like this over here and like this over here. Right? So basically your current remains the same. Your voltage has changed. Just changed your voltage. Now to reach this again, there's another way. You have to go like this till here. And you have to come back like this. And many times this is what they want. Like this is your best. So this is for a reference change. All right. Any queries in this? Sorry.
Sir, during that, does it mean it should reach the new operating point in one switching cycle, or the new switching cycle time will be more?
There's some time duration where this is T on and this is T off, right? Okay, but this T on plus T off, they will usually be more than your switching period. They will usually be more than your switching period. So this T on and T off have to be selected in such a manner. Okay, Arun, you were saying something?
No, sir, it is clear.
So in this part, it will be operating for a time period T, right? It will be on for some time dt or from 1 minus dt. It will be on for another d, maybe d2t. This will be off for 1 minus d2t. But when you want this time optimal control, you will have some particular t on and some particular t off. In most cases, that will be more than your capital T. Let me just drink water once. Okay. So now, how will we know what should be your T on and what should be your T off? That is a thing, right? We need to know what is your T on, what is your T off. What is done is, we have what is known as a switching surface. Given like this, assume it's a straight line where its equation is given by sigma is equal to kp into vref minus v0 plus iref minus il. This is your switching surface, and this has a gain of minus kp. So this would be the same point. So this point would intersect. So if you want it to work in such a fashion, there is one particular kp which you must select such that it will hit it, and then the switch will turn off, and then it will reach this value. So this is that kp which you need. And this kp will determine the slope of your line. The slope. If you change your kp, your slope can change. Right? And you may ask, like you have told about PID controller. Like we started and we spent 30 minutes, half an hour just understanding PID controller, right? Now, where is the integrator? Where is the derivative? Now, what we consider is that the dynamics of your integrator is very slow. Your integrator dynamics, that is your integrator, we consider them, they are very slow. And that is true also, right? Because we want your integrator to work. It has its impact, it does its main job in steady state. In the transient time also, it does some work. It's not that it is not there. It's not that its effect is not there at all. But its effect is negligible as compared to your proportional and as compared to your derivative. So that is why we ignore the Ki when we are doing these calculations, because it will make it more complicated. It will be hard to represent, etc. So we are ignoring the dynamics of Ki. Okay, so Ki dynamics are ignored. Now, what about your derivative? So this is what sigma is equal to Kp into Vref minus V0 plus Iref minus IL. right? Now, what is your IREF? Your IREF is a load current. So your sigma is what? Kp into Vref minus V0 plus I output minus IL. And what is your I output? That is your IC. So this is Kp into Vref minus V0 plus your, this is your not IC. Okay, let me show you. That makes sense here. So this is your IL. This is your I naught. This is your IC, right? So your IL minus I naught, this is equal to your IC, right? Your IL minus I naught is equal to your IC. Now we have your I naught minus IL. So this will be equal to minus of IC. This is equal to minus of IC. Okay. Now, usually Vref is fixed. Okay. So your IC is what? C into dV0 by dt. So your IC can also be written as C into d of V0 minus Vref upon dt, because your Vref is fixed, so derivative of dVref is 0, right? So you write your sigma, that is equal to Kp into Vref minus V0 minus of C d of V0 minus Vref by dt. So your sigma is Kp into Vref minus V0 plus C into d of Vref minus V0 by dt, right? And this is set as your Kd. This is set as your Kd. So now what we have done, we have linked Kp, we have linked Kd, and we have told that the Ki value, its impact is very less in the transient. So we consider it only for the steady state. And for steady state, sir has given a formula for Ki, that is, I think, pi into 1 minus d upon 10 L or something. I'm not sure. We'll have to check this. This needs to be checked. Okay. Any questions in this part? Or you want me to repeat it? Because this is complicated stuff. Okay, so now what we have done is we have linked the switching surface, that is this surface, we have linked it to your PID controller structure. We have kind of, drawn parallels with your PID controller and your switching surface. So now what we'd like to consider is load change. You guys are familiar. Like, why do you think there'll be a load change? Like, could you give a practical example of where you have experienced a load change, or where in your life, in your house, or in your college, where do you think load change happens? Could you give an example? Hmm?
When we suddenly switch on a motor, the lights will be somewhat dim because of the reduction in voltage.
Okay. Yeah, correct. Because of the reduction in voltage. Okay. So there's a dip in your voltage. Very good. Then any other example? What about Parvati and Joshi? You have no load changes. Everything is fixed in your life. You can even send a message. Okay, so load change, I guess you have to be more observant and you'll see more examples of load changes happening in your life. So there is also something known as load shedding, which you guys have known. That is the non-critical loads. The electricity board will sometimes cut off power to that, such that the main loads they are functioning, right? Because it is not able to supply that much amount of current. Okay, that those are some other things. But there is a concept that is the load changes. It will fluctuate, it will change continuously. So when your load changes, your operating point of your system is also changing. So now, like, the objective which I'm trying to bring out to you guys is this, what you say, this load change is a fact. It happens. That is, this load change is happening. But can you tell me when do I need to change my voltage? Where is it required in my life or in any case that my voltage has to change? What could be the examples? Which you know, like based on your projects, based on the things you have studied, etc. Where do you think that the voltage has to change?
In speed control of induction motor, like V by F control, we have to change voltage and frequency.
Yes, very good. Speed control of induction motor. You can have also armature control of DC motor, right? So we are controlling the armature voltage. Very good. Then, what are the examples could be there? Okay, so we have understood that the voltage. Also, there are examples in our real practical life where we want our operating reference voltage to change. Okay, so that also is a practical thing. This is not just any fictitious thing. Now there is something which you all use. Many of us are addicted to mobile phones. Okay, like we have nowadays, people have screen times of 5 hours, 2 hours, 3 hours per day. Okay, so like when I see my digital well-being, it's like it's very scary how much time I spend on my phone. Okay, so phone is something which we all are using a lot. Mobile phone we are using a lot. So you have in your phone, you have what is known as a processor. Okay, there are various intricate, many details are there, but as sir has told, you have a processor in your phone. Okay, it will have various things, right? It has various chips, various pins. You all have seen various ICs, etc. So they have various pins. Assume your processor also has various pins. Now, for your processor to work, since it is an active device, it needs a supply. And that supply we term it as VDD. Okay, that supply we term it as VDD. Now, if you would have seen, say, microcontroller chips or various of these integrated circuit chips, digital logics, all that, you will have VDD at different points. Here you'll have a VDD, here you'll have a VDD, here you'll have a VDD, etc. Okay, there are different VDDs are there. Now there could be a case that all these VDDs are connected from the same point. They're receiving power from the same point. You have some converter here, which is giving you power, which is setting your VDD. It could be the case. Okay, since we are new to this and we are trying to learn, let us consider the simple case that you have some input voltage to your converter and that is generating your VDD. Okay, very good. So we have an input voltage to a converter. We are trying to learn a very practical example. of a system which we all use extensively, and then that is generating some VDD. Now, many times your phone, if you notice your phone, you're not using it. Like hopefully you don't have a chronic addiction to the phone. There are times in your day where you are leaving your phone at the side and you are studying, taking notes, or maybe you're reading a book, or maybe you're attending a class where your phone is there. It is it is like kind of in idle state, idle state, or in sleep mode, sort of. It's in sleep mode. Let us assume. So what happens at that time is you don't want your phone to drain your battery in that case. Right now we have a like 80-watt charger also, so you can charge your phone in 10 minutes also. Is very good and nice. But still, you don't want to constantly connect it to the charger, right? You want your battery life to be good, everything. So at a time when you're not using your phone actively, huh, you don't want it to drain lots of power. You don't want it to drain lots of energy from your battery. So that power which it takes, that dynamic power, is proportional to your VDD square into your frequency. Your frequency. You have certain clock frequency, etc. Right? Like your processor, the microprocessor. Also, you would have studied in your electrical engineering. That microprocessor has a certain clock, and based on that clock, the instructions are executed. So certain instructions will take 3 clock cycles. Certain instructions will take 4 clock cycles. So those are like your machine cycles, etc. Right? So if you want your cycles to be if you want your tasks to finish fast, what you have to do is you have to increase your switching frequency. If you increase your switching frequency, your task will happen very fast. Okay, but if you increase your switching frequency, what will happen? Your dynamic power loss is increasing. So that is one trade-off which you have to handle. Another thing is your switching frequency you can increase, no doubt, but there's a certain delay, and that delay we approximate it, or they have approximated it, or they have seen that is inversely proportional to your VDD. That is, if your VDD is low, then your delay is high. If your supply voltage is low, then your delay is high to your transistor. So it will take more time. It will take more time for computation. But if you want to reduce that delay and if you want to compute a task fast, then you have to increase your VDD. But when you increase your VDD, your power consumption is more and your battery will drain much faster. Okay, so this is like a simple approximation of what happens for us to understand. So basically what is there? Your VDD can increase your speed of computation, but when you do that, your dynamic power loss becomes more, your battery will discharge more. So what you want to happen is you want your VDD to be adjustable. That is, when suppose you are left your phone, like when you're sleeping, hopefully you don't sleep with your phones. When your phone is away from you, when you're sleeping, your phone is idle. So it will be consuming some amount of, it will be doing some amount of work, that it will be waiting for your notifications. If you get a phone call, it should be willing to respond. So it will require some power, but it will not require very intensive power. So that time your VDD would be low. Let us say in your night time, when you're sleeping, etc., your phone is idle. Then suppose you're watching a movie, or you're seeing a listening to some YouTube video, or you're playing a game. That time you want it to run very fast. So that time your VDD has to increase. So this VDD has to increase, reduce based on your requirements. Okay. So that is known as your dynamic voltage scaling. Which is known as your DVS. Okay. And how do you adjust that? Through this converter. Through this converter, you will control it in such a manner that your VDD will get adjusted. Okay. So any doubts in all this, or we can start with the questions?
It is clear, sir.
Okay. Okay, so let's start with the questions. Okay, so from this, can you tell me, this for PID controller, what are the statements which are true? What statements do you think are false?
When Kp decreases, steady state error will increase.
Good. Good.
And when Kp decreases, settling when Kp increases, settling time has minimal effect.
Yeah, it has minimal effect. So we
So,
cannot directly say it increases, reduces, so we can ignore it. Okay, we'll say settling time doesn't change.
and overshoot will
Percentile
decrease.
overshoot also reduce.
Okay, good. Percentage overshoot reduces. Okay.
Then that slope of the switching surface will also change. It is minus Kp.
Okay. Yes, good. So this is regarding your proportional controlling. What are the effects of your proportional controlling? So very good, you have understood this. Let us go to the next question. What is the effect of the derivative gain?
Steady state error has minimal effect. So first one is false.
Okay.
Settling time will decrease and overshoot will decrease.
Good, good.
Fourth one is wrong. An ideal derivative is not practically realizable.
Okay, okay. Great. So yeah, now you're doing fast. Very nice. Okay. The next question. So this is your DVS, dynamic voltage scaling, which we just considered now. So first option is true. Okay. Next option.
It is directly proportional to frequency and directly proportional to square of VDD.
Okay.
So second one is correct.
Okay.
And computational delay is inversely proportional to VDD. So third one is wrong.
Okay.
Fourth one is correct.
Okay.
And the last one is also correct.
Okay. Okay. Yes. Yes. Proportional to the square. Yeah. Yeah. Okay. Very good. Joshi, you want to say something? Okay. Okay. So let us consider load transient optimal control. Okay. We have to solve this question. Let's go for this question. Question 4. So we have a load transient optimal control. Now, how do we do that? So what is required, what is provided to us is 1. V in is 5 volt, V reference is 3.3 volt, L is 200 nanohenry, C is 100 microfarad, load step of 10 ampere. So we have V in is 5 volt, V reference is 3.3 volt, L is 200 nanohenry, C is 100 microfarad, and your load step delta I naught is equal to 10 ampere. So now it depends on your memory. I guess you guys are smart. You should memorize these formulas. Ideally, perhaps those hints might be given also in your exam, but can try to remember the formula. So what is the formula? So what you have to find is, you have to find out what is there. Peak current IP. Okay. This you need to find out. You need to find out the recovery time TR. Recovery time TR. Then you need to find voltage undershoot. Voltage undershoot. Delta V naught. And your gain. KP. This you need to find out. All these is you need to find out. Okay. So now, as we have seen before, this is your V output, this is your IL, right? This is the on period, this is your off period. On, off. This is your VREF. This is your I naught 1. Now you have to go to I naught 2. So this change, this is your delta I naught. This is your delta I naught which was provided to you. Okay. Now your next condition is here going like this and like this. So this is your on time. This is your off time. Right? So you want it to go like this to this. So this is your on time trajectory. This is your off time trajectory. And your line could be something like this. This could be your line, but this is your minus KP. Okay, this is your minus KP. Now, what happens when we do these calculations? We sort of neglect the ripple. Current ripple we neglect, voltage ripple we neglect, because those are very small as compared to your change in your load. Right? So delta I naught has changed by 5 ampere, right? Or 10 ampere in this case. 10 ampere. Okay, so it has changed a lot. Now, what do we look at is, it would reach some, if you would have seen a derivation, it reaches a point that is your V1 and your I1. This is a point it reaches. And then it will come back to this point. So it goes from here and comes back here. But it will reach some intermediate point where your voltage is V1, I1. Voltage is V1, current is I1. So this change, this is your peak current. Okay. This is your peak current. That is how much it has exceeded your next condition, how much it has increased. That is your peak current. And what do you say? This is your voltage undershoot. That is, your voltage had to be at VREF only, but it went low. It went less than Vref. It reached some point V1. So how much your voltage has reduced? That is your delta V naught. That is known as your voltage undershoot. Okay. And then this is your phase plane. Phase plane means your time information is not provided, right? Here you don't know how much is your time duration. You don't know. But we want that time to be less. We want that time to not be a lot. So that is known as your recovery time TR. Like how much time it will take to go from here to come back all the way over here. That is known as your recovery time TR. Okay. So for those, there are certain formulas which you should remember. So your I peak is equal to square root of D into delta I naught. Right? I peak is square root of D into delta I naught. So what is your D? Can you tell me what is your D?
.66.
D is 0.66. Okay, so what is square root of D into delta I naught?
8.12.
Okay, 8.12 ampere. Okay. So this is done. Next is you want to find your recovery time. Your recovery time is given by the formula L into delta I naught upon V naught into square root of D upon 1 minus square root of D. So what is this recovery time given by? What is the value which you are getting?
.62 microseconds.
Okay, so if you will see, this is not like your time period. Your time period is not provided, but usually you will not have a time period exactly like 2.62 microseconds, something like that. It won't be there. Okay, but this is like kind of like your recovery time. Okay.
Sir, V0,
Yes.
sir, what is the value of V0?
Your VREF 3.3 volt. Because in the operation you want your output voltage to be at the reference voltage. So that is your V0. Okay. What is your delta V naught? Delta V naught is ZC square into delta I naught square into D upon 1 minus D into turn V net. No, this is V naught. V naught. Yeah. Okay. So what is your ZC square? Your ZC is your characteristic impedance that actually is equal to square root of omega L by omega C. The square root of L upon C. I think you would have come across this in power systems when you have studied transmission lines, etc. There's something known as a characteristic impedance which they use while modeling a transmission line. So that is known as your characteristic impedance, that is ZC. Perhaps you may have come across it in different places. But why you look at ZC equal to square of LC is L upon C is, you know that if you have L upon C, that means it has a dimension of ohm square. That's the way you correlate. That's the way you check your expressions. Okay, so this ZC equal to square of L by C is a very useful way to understand that the derivations which you have derived, they are correct. Dimensionally, are they correct or not? Okay, so that's one thing I'd like you to keep in mind. Okay, so can you tell me what is your ZC?
0.0447.
Sorry?
0.0447.
Point not 0.0447. Okay. All right. So then we find out what is this value.
But I got 0.26.
Okay. What about others?
Delta V0 is I got 0.0588.
Okay. Could you both check once more? Let's hope Joshi will give the correct answer.
Sir, in the denominator, is it V0 or 2V0?
Oh, it should be 2 easy, right? No, sorry. 2V0. Let me write in a new page better. Delta V naught ZC square delta I naught square 2V naught into D upon 1 minus D. How much is this?
Uh, 0.0588.
0.0588. Okay, what about Parvati?
I got 0.13.
Okay. I think Joshi is not helping us. That's why we are stuck. Let us see. Your delta V naught is ZC square, that is actually L upon 2C V naught delta I naught square into D upon 1 minus D. Delta V naught is L is 200 nanos, 210 to the power minus 9. 2 into C, so 100 into 10 to the power minus 6. V naught is 3.3. Delta I naught square is 10 square. D is 0.66. 1 minus 0.66. This 0.34. So, how do we conclude this? Let us. Should this gets cancelled, this gets cancelled, this gets cancelled, this gets cancelled. Delta V naught is 10 to the power minus 3.3.3 into 100. So this is into 6 upon 0.34. So delta V naught is 0.1 into 3.3 into 6 upon 3.4.
Yes, sir. I also got 0.058.
0.058. Okay. Is this what 0.05 calculator summaries? You have 0.126 divided by 3.3 into 3.4. It's 0.0535, no? Put 2. Did I input 2 or 2 I input?
Instead of 0.66, you have taken only one decimal.
Oh, okay. This. Okay, 0.588. No, sorry. Sorry. One. 0.1 into 6.6, right? Point. 0.0588. Is this what you want to get?
Yes, sir. 0.058.
Okay. Okay, good. Okay. So then we'll try that PID controller thing. Let's try. Just one minute. Okay. Let us try to understand PID. SIMULINK block will make. And then I just define some parameters. Plan transfer function. So S is my transfer function variable. So D underscore D. Let us take it to a simple second order plant. Here omega n is natural frequency. Let us say 1 in 3. Zeta in time. So till this week 10, have you received all the assignment solutions?
Sir, didn't hear you.
Oh, sorry. Till week 10, have you received your assignment solutions?
No, sir. Till 8th only we got.
Okay. Good. But now you have to submit week 11 assignment, right?
Yes, sir.
And when is
And
your
one mail came that we cannot use calculators. We have to use calculator and the system.
yeah. That's the way. You have to use the gate calculator. So
Take no more time, sir.
yeah. But you have given gate, right? Yeah. That's why I prefer, like, when you're solving the assignments and when you're solving your sums, etc., you try to minimize using the calculator. Like in this case, also the example which I showed, I did the basic, you know, elimination, 10 to power minus 9, all those things eliminated. And then you do this, you make it easy and then you calculate. That would save your time. That you can do. And further, what is your how to say? When is your exam? On which date?
I registered for November 2nd.
Oh, my birthday. Acha. And others?
Yes, sir, November 2nd. While registering, it was shown as November 2nd, but hall
Oh.
ticket is not released yet.
Oh, okay. Acha.
Now
So
only October 15th date has come. November 2nd hall ticket didn't release.
oh, October 15 also there's a test.
Yes, sir.
But that's for different subject.
Yes, sir. I have another exam on October 26th, Sunday.
Oh, okay. Mm-hmm. 26 and 15. Okay. Yeah, all the best for you guys. Yeah. So this is your last semester of coursework, right? Or you have one more semester of coursework?
Last semester.
Last one.
Okay. Then no more exams in life.
Then
Mm.
one NPTEL and MTech exam is there, and
Oh.
one self-study.
Oh, yeah. Yeah, these are your last exams. So don't give it your best. Mhm. Okay. So we'll start defining the transfer function. So I'm giving it the transfer function of a second order system. This is a transfer function. Let me check whether it is coming correctly. Okay, made a mistake. 2s. Okay, so this is your ideal, this is like your second order system transfer function. It can be represented like this. So now let us make a SIMULINK file. This is your SIMULINK start page. Let us say a blank model. It is very slow. So after these tests and exams, you have to give comprehensive viva also.
6 months.
6 months you have to give.
Yes, sir. There is a comprehensive exam and a comprehensive viva after this.
And how is it usually like? Is it tough or how it is?
Basically, we have to select that subjects, two
Okay.
core subjects, and then two subjects from the engineering basics like circuit theory or mathematics,
Okay.
machines. Like then three course modules from research area like power electronics or power system or control system.
Oh, okay. Okay.
Then based on that,
For,
they will prepare question paper.
Okay. Hmm.
for me, only comprehensive Viva will be there, and
Okay.
they will ask about only the coursework and about my research work
Oh,
till what I have completed by that time.
okay. Yours is a bit easier.
Externals will ask many questions, sir.
Yeah. Yeah, all the best for those things also. Before joining PhD, many people don't know all this is there. So there's transfer function. So function. So this is your transfer function block. Let me bring it here. This is here. So I can just give it g underscore p. Very slow. It has got a transfer function. So let us, what we will do is, we will give a step input. Let us say it goes from 0. Step time, let us say 1. Initial value 0 to 1. If we good. Let us put a scope. So this is your input connected here. This is your output. Let us run it once. Let me open the scope. Let us see the output being displayed on the scope. So this is your output. This is your input and output. Just let me just do one thing. It was taking too much time here. We make the time to be 2. We run. We'll make it best to this. Let us step happen at 0.1. This be 0.2. Let me run it now. So this is your plant. So you can see that it is working. Okay, and if you will notice carefully, you will see that the lines are not smooth. It is not smooth. It should not look like this. So to overcome this, what you should do is, you should go to your modeling, model settings. Go over here. So then you reduce this maximum step size. Let me make it 1e minus 4. The selective tolerance, make it 1e minus 5. Let me apply. Let me check. We run it now. Now, if you will see, it is looking more smooth. Okay. So that is because your step size is big. If your step size is big, then it will solve for after more duration. It will not be so accurate. The more smaller you make your step size, the more accurate your simulations will be. Okay, this you may know, but I'm just reinforcing it. Okay, so this is your plant. We have checked that your plant is giving the response of a second order system as we have defined it. Okay, so when you usually do your projects or your simulations, etc., it's best that you verify each small block part by part, and then you integrate finally. Otherwise, what happens many times is you make the entire thing completely and then you just say it doesn't work. Okay, so you just try to verify block by block is it working, and then you integrate it into your entire complete system. Okay, that's a good way, recommended way. Hmm. So now what I have, this is my output. This is my output, right? This is my output, and this is my reference. Okay, let me delete this. So now in my closed loop, what I want to do is I will have a subtract block. Subtract block I will add. So this is my reference, which is subtracted from my output, right? Now, let me just add a gain. Let me add a gain of 2. Okay. Now let us check. Let me run it. If you will notice, there is some steady state error. I have brought it into closed loop. I have used one gain, but I have some steady state error. This is because I've just used proportional gain. Okay, we have just considered proportional gain. Now what we will do is, if you will see this error, it is between 0.65 to 1. So your error is, let us say it is around approximately 0.35. Your error, steady state error is 0.35. Let me increase the gain to 10. Or let me make it 20. So now, what you will see, your error has reduced. Okay, your error is reduced. Your percentage overshoot also has increased. Your percentage overshoot also has increased, but your error is reduced. Settling time is almost close, comparable it is. Okay, so this is the part of your proportional control. That's why we are studying it. Let us practically implement and let us check it. Okay, so we have seen the proportional controller also is working fine. Let us see something else. This is your error, right? This is your error. Let me even, how do I get the error? Three. We have made three things. So this is your error. Let me also plot it separately. View, layout, three. So this is my reference. This is how my output is changing. This is how my error is changing. There you go. It's the problem. The zoom feature is not working here carefully, properly. Okay. So this, I hope you got a point. That is, your error also changes as your reference has suddenly changed. Ah, so the error also changes accordingly. And if you will notice that there is some error present. Some error is present. The error has now become zero. So what I'll do is, okay, I will do eliminate this. So this is my proportional part. Now I'll add an integrator. Integrator. Just going by 1 by s, right? Now make it bigger. Yeah, I connect the error here. I'll add a gain, which is my integrator gain. 1. And I'll connect. Okay, let me make this 2 so that you can see. If you remember, let me run it for 2. So, okay, so let me tell step by step. So when I only have proportional gain of 2, let me again rerun it and show you the output. Let us just check it. We'll see how it looks like. So if you run it, you will notice there is some error. There is some error is present. Your reference has changed. Your output takes time to change. Your error suddenly starts from a large value. And as I was trying to draw, this is how your error looks like. Okay, this is for a proportional controller. Now, because there is this steady state error, what I'll do is I'll add the integrator. So I'm adding an integrator. The gain is just 1. Now let us run it and check. Gain has, your integrator has still not corrected it. Okay, integrator gain is very low. Let me increase the gain. Okay. So what is happening is your integrator is slowly reducing the error and your output slowly is reaching your 1. Okay, so this is how the integrator is affecting your dynamics. It is making your error to become 0. Okay. And what I'd like to plot is, let us say, let us add one more block, view, layout, 4. Okay. to make it more easier to visualize, let us use layout, sorry. Number of inputs, let us make it 4. Apply. Okay. This your reference, it's your output, this your error. Okay. Let me mark your reference and output. So this is your reference, this is your output. They come here. Over here, let me show the error. Okay. Over here, let me show the KP contribution. So this is your proportional part. And this is your integrator part, right? Now let us run it and check. So if you will notice, your proportional part finally settles at 0. But your integrator part does not settle at 0. It settles at close to 1. Right? And your proportional follows your error. It follows your error. As your error is curve looks, your proportional curve is just a scaled version of your error. Okay, so this is your proportional contribution. This is the contribution of your integrator. Now, is there any questions till this point? Anything is difficult, anything hard to understand, you let me know. No doubts. Wow. Okay, very good. No doubts. Okay. So now what we will do is we will add our derivative. Let us add derivative. See how the derivative will look like. Okay. So for derivative, what I need a derivative block. Let us see if derivative block is there. This there. I have not used this as such. Ah, okay. Let me try this block. I have not used it. Let us try it. Or take a risk. Let us say we have LTI transfer function, LTI system. So your numerator will be 1, denominator will just be 0. Let us check whether it accepts this. Okay. Is it showing question mark? Let us run this. Okay, so it should not be non-zero because it becomes an derivative. So we cannot do that. So let us use it as some 1 upon tau s plus 1. So tau, let us take it to be like, let us take tau to be 1 and there's also 1. Let us run it like this now. This iterative action. And let us give some gain.
Sir, can we use that KDS by 1 plus S TOD with a very small TOD?
Yes, TOD can be very small. Let us, you want, that can be 1e minus 6 also, very small. Now, this is your derivative gain. For the time being, let us keep it 1. Let us keep it 1. So I've not plotted the derivative also. Clumsy actually. So let us have a mux Proportional part, let me bring here. Derivative also, let me bring from here only and show over here. The derivative part. Let us run it. So, legend. So if you will, the yellow one is your proportional part, the blue one is your derivative part. This is your derivative action. One more thing, let me just change your time because it is not clearly visible for you guys. Let me make step to happen at point 0.01. This time of simulation to be just be 0.05. Let us check it now. Yeah. So if you can see, when your reference changes, your error has increased rapidly. The proportional part also increases, your derivative part also increases, but your integrator is taking time. Your integrator is taking time. And as your error is changing, your proportional is in phase with your error, and your derivative has slightly similar action as well. Because what is your derivative? It is the time derivative of this, right? So it is coming like this. But because this is not an ideal derivative, you added that filter over that tau s plus 1, it looks like this. There's a slight delay, but it
Sir,
kind
can
of,
you show the derivative block once again in the transfer function?
this one,
And the transfer function used for derivative.
this one, this one, this one.
This one, that block.
This LKI block.
So is the numerator 1, 0 or simply 1 because it is KDS?
Oh, I'm so sorry. This way 1, 0, sorry. Correct. Very good. 1, 0, comma. Yes. Let us check this. Yeah, very good thing. KDS. Right. Let's check it. Okay, your derivative is too high. Let us reduce your derivative to make it 1e minus 3. Let's check now. Okay, so what is happening is your derivative has a very huge kick. It is not visible. The derivative is not clearly visible. So let me do something else. We make this 3. Take this error over here. And derivative that we put over here. We delete this. It's your proportional part. Okay, so I put up the interchange. It can. Okay, fine. So if you will see, so yellow is your reference, blue is your output, orange is your error. Okay. So here your derivative is a very large spike. Your derivative is a very large spike. Your proportional is in phase with your error, and your integrator is slowly accumulating the error and finally reaching a value such that your steady state error is 0. It will slowly become 0. Now what I can do is, since your derivative gain is it may be low, but your filter, your tau is very small. Let us increase your tau filter value. Let us make it 1e minus 3. 1e minus 2. Let us see how it looks. So now your derivative jump is not so high. It is not that high, right? And this is your derivative action. And if you see, your derivative action becomes close to zero quite quickly, because your proportional is what? Proportional into error. But your derivative is your derivative gain into your change in your error. So in this point, when your error is not changing much, your derivative value becomes zero, almost zero, very low. So it has negligible impact on your performance. But when your reference changes suddenly and your error changes suddenly, that is during your dynamic transient part, that time your derivative has a large impact. It has a large impact. Okay. So is this clear?
Yes, sir, it is clear.
Okay. Okay then. So if there are no other questions, then we can meet next week for week 12. And that is on Tuesday. And on Thursday will be the summary session. Okay. Okay. So then I'll end the meeting then.
Thank you, sir.
Thank you for joining.